Good day, Carrie Lisse here from the Interstellar Probe, or ISP, Dust and Astrophysics Science Teams. I'm here today to give you all a sense of exciting and unique and transformative science that ISP can do by taking two new instruments out from the heliosphere, through the heliopause and the heliosheath, and into the nearby galaxy. Those three regions are illustrated here in the picture on this cover slide, showing regions 1, 2, and 3, where ISP will be doing all its exciting science. So let's move on and see what kind of science it can do. Well, as a highlight, there's three different populations of dust we can expect in each of these regions. One is what we call the circumsolar dust, or the zodiacal cloud. That's dust around our star, which is originating from the asteroids grinding and comets subliming and Kuiper Belt object surfaces getting scoured by ISM dust, and also collisions. And we know that there is dust in our own system, as well as we see dust disks around other stars. And that gets illustrated on the left. In the top left are a series of Hubble images of dust disks around other stars. And in the bottom left is an infrared image of our sky looking outwards from the Earth. And we see dust emission, both from the zodiacal light, that's the big Z or blue, lightning blue boomerang you see in this plot, the galactic coordinates, and the galaxy itself on the x-axis in the bright red and yellow. In the center, once we've actually gotten through the heliosphere and gotten to the heliopause and the heliosheath at the very edge, we expect a lot of dust in the bow shock that is plowing up as the solar system moves through the galaxy in the interstellar medium. And here we see 5 examples of extreme outliers of this behavior from Mira and LL Ori, Zeta Oph, Beta BZ Cam, and IRC 10216. And we see lots of continuum emission, both in scattered light from the star and thermal emission from heat radiation from dust at these boundaries. And so what is ours like? We don't think our boundaries is extreme, but we do think there's a lot of dust there, and it should be radiating, we should be able to sense it, as well as pick some of it up. Finally, when we merge into the local interstellar medium, nearby galaxy, we're going to again see a lot of dust. We know it's there from that background image I showed you, the 25 micron image. We know that there is dust emitting there. And in the bottom right shows you our best example of remote sensing measurements of the clouds we think are nearby. And we think there's a lot of variety and interesting behavior there. And we're going to actually be able to sense for the very first time directly what's going on in these clouds. So I just gave you a whirlwind tour. Let's go into a little bit more detail. Our dusty journey starts with a major ISP science goal using its unique trajectory to study the circumsolar dust in the solar system, also known as the Zodi cloud or the Zodi. I'm going to use all the terms interchangeably. We know from visible infrared observations that we see this debris disks, or circumsolar disks, dust disks, around lots of other stars. They have rings and they have gaps. I'll show you a picture of that in a minute or two. Disks are associated with aggregating planets, subliming comets, and colliding asteroids, as I mentioned. And we see dust in debris disk dust in Kuiper belts, mainly. The pictures I showed you from Hubble are all Kuiper belt dust. That's because Kuiper belts are at the very edges of the original solar systems as they're forming, and every system has an edge, just by definition. So we expect that those dust to be common. Rarer are the warm dust we see down deep in what we think are asteroid belts. And they may be rare because it's not common to have dynamically stable asteroid belts around a star, or they could be rare because it's just very hard to distinguish them from because they're close into the star at the distances we see other stars. We know in our own system, getting back home, from Helios, Pioneer 10, and Clementine, that our system is filled with dust. It's been sampled, it's been picked up. So that's in the inner system. Only just recently has New Horizons, flying out past Pluto and MU69/Arrokoth, actually detected outer system dust, our own Kuiper belt dust, for the very, very first time. But now we know it's there. I'll talk about that later too. Finally, ISP will probe the 3D structure of our own cloud. As it goes through the cloud, it's going to measure different amounts of cloud in front of it. I like to think of this as, for example, if you were walking through a cloud or a fog bank yourself, and it's very opaque, it's thick, but as you walk through it, it gets thinner and thinner, and finally you break free into clear sky. And if you're very smart, you can actually invert those measurements of looking forward into the amount of stuff, material between you and clear. And you can invert that in order to get the 3D structure of the cloud. And we're going to do that with ISP as we transit through the whole cloud. So here illustrated directly are the debris disks in our solar system. On the left, you see the greenish and the reddish spots. Those are the asteroids in the main belt and also the near-Earth asteroids. And this is a system which we know grinds, we know collides, we know spits out dust. And just recently, we've seen from Bennu, at OSIRIS-REx at Bennu, that we've actually seen an asteroid just throwing out dust on its very own. No collisions as far as we know. So asteroids form dust. And this dust is near the sun, so it's warm. So we know that we have some of this here. We know it's nowhere near as dense as what we see around those really bright other stars, those outliers, those beautiful images I showed you with Hubble, but we know we have a good amount of it here. And you know, when you look up at the sky at night, it's there too, because 10 times an hour or so on an average night, much more during a storm or a shower, you will see meteors streaking through our sky as little pieces of intersystem dust accrete onto the Earth. In the center, you see our Kuiper Belt objects. And we now know from New Horizons that there is dust associated with them. And in fact, the interesting thing, I'll talk about this some more later too, is that we now think that 97, 98% of all the dust orbiting around the sun is actually not in the inner system, even though that dominates because we're immersed in it, because it's very hot nearby, but it's actually in the Kuiper Belt. And we're only just beginning to sense this. We've had one dust counter fly through this on one chord. If you add the two of these together, you get the image on the right, our best synthetic model currently of what we think the dust disk for our own system looks like if you're in the plane of the disk and you're looking back. And this is important because we think this is what ISP could measure when it gets out very, very far away, 500 to 1,000 AU from the sun, some many decades hence from now. Going back home, when we look out from the night sky and we look out with thermal infrared eyes, this is what we see. This isn't galactic coordinates, so the galaxy is the beautiful yellowish, reddish, very bright system along the x-axis, along the horizontal axis. And this is, what you're seeing is hot thermal emission from dust in our galaxy. And you're looking all the way through the galaxy, which is hundreds of thousands of light years across, so it looks relatively bright. A lot of the dust stacks up. Closer to home is what I like to call the beautiful lightning blue Z of Zorro, or the Zodi, or if you will prefer, a boomerang. And this is the dust in our system. It is concentrated on the ecliptic plane, which goes into the Z formation in these coordinate systems. And we're immersed in this. And it is all around us. And it envelops the sky and covers it up. And that's good and that's bad. It tells us a lot about the dust, but it also obscures some very important signals that I'll get into later. If you want to see this emission at night, if you were in a dark sky, like the picture in the upper right you see in Hawaii, you wait until the sun goes down, and right after the sun goes down, you'll see a beautiful kind of parabolic arc, archy shape, almost pointing from where the sun went down up into the sky. This is sunlight scattered below the horizon, scattered off the dust in the dust disk surrounding the sun, and then back to your eye. So we know it's there. Further out, going into more terra incognito, or space incognito, is the dust that we think could be in the heliosheath and the heliopause, the very edges of our system. And why do we think there's dust there? Well, when we look at 5 extraordinary candidates, very large O and B stars, so much, much hotter than the sun, much bigger and putting out more wind than the sun. But when we look at them, we see them having, for all the life of us, look like bow shocks, look like structures due to material plowing up in front of them as these systems move through the local interstellar medium. The bow shocks have various structures, some almost bubbles, others more arcuate. But what we see here clearly is scattered light from this local star scattering off of material in these shocks, in these boundary regions, and to our telescope. We also see direct heat thermal emission at longer wavelengths, wavelengths that we will be able to detect from ISP. And what we have here are very good evidence that there is dusty material building up in a boundary region around these stars as they move through the interstellar medium. Same thing should be happening with our star, maybe orders of magnitude less dense and less energetic, but still should be happening there. We won't know for sure until we actually go there and just simply try to sample pieces of dust in this region. And that's simple and straightforward enough for ISP to do with a good dust analyzer instrument I'll talk about later. On the lower right, I want to introduce you to the idea that the structure of our own bow shock, our own heliosheath and pause, could have various forms. We think it could be spherical if it was a stellar wind dominated model where just the wind is just blowing out so fast and hard with high enough pressure and energy that it, in all directions from the star, that it forms a bubble. Or in the lower left, it could be more comet-like shape where it's dominated by the motion through the ISM and also by the local magnetic fields draping around the envelope, the heliosphere. So we don't know for sure. What we can say, we go to the next slide, is that current models look more like a little bit of a combination of both of these. If you look in the lower center, the croissant, or I like to call it the grub model, looks a lot like a bubble but with some tails and drape magnetic fields across of it. What's interesting to know is that all the models you're seeing here, and I'm not an expert to go into them other than to say is that there's been a lot of detailed, interesting analysis due to the results from the IBEX mission, from the Voyagers, from our understanding of what's going on in the outer edges of our heliosphere. The important thing to point out here is all these models are for simple plasmas, no dust. And the physics of dusty plasmas, once you start getting appreciable amounts of dust, is dramatically different, and it will change the models extraordinarily. None of these models have dust in them because we simply don't know anything about the dust in these edges of the system, in the heliosphere, in the heliosheath, and the heliopause. We do not understand and have no constraints on the amount of dust there. So that simply by just taking ISP through this layer and being sensitive to the dust, by being able to pick up pieces of dust and measure them, or by using remote sensing to actually measure any sort of scattered light and thermal emission from them, we can do an extraordinary simple piece of science by even an order of magnitude estimate for the amount of dust there. And finally, once we get through this heliosheath and pause region, this boundary region, and get into the nearby galaxy, then we're going to be able to do some even more fantastic science. On the left, you see our best understanding from remote sensing of what we think the local galactic dust clouds look like and their structure. The sun is the yellowish-orange spot at the center. The sun and solar system, you and I, are moving to the upper right in this system, about 26 kilometers per second relative to the local galactic material. And the local galactic material is in the light and medium blue and black and has structure. What you're seeing here is not just a simple artist's impression, but our best understanding of what we think the dust density variations are in the local dust clouds. And the sun looks like it's at the edge of a high density region and possibly going into a low density region within the next few thousand years, and ISP may emerge right into that. Now, that all being said, this is just a map, if you will, of the number of dust particles, the dust spatial density. On the right is a somewhat complicated plot, but I'm going to steer it through you quickly because you'll have time to look at it in leisure with this recorded talk, is that there is a large current disconnect between what we predict for the kind and quantity of these dust particles from remote sensing. Those are the curves on the left, the dashed lines of the total solid line, and what we measure inside of the heliosheath and heliopause. So as far as Jupiter and Saturn from the sun, and those are the blue squares. And this is a size frequency plot. So lots of complicated units on the vertical axis, but close to simply just saying is the number of particles per unit mass bin per volume versus the particle size on the horizontal axis. And you'll see that the predicts for silicaceous and carbonaceous dust, when added together, give you a increasing towards larger masses kind of frequency curve, and then a steep drop off at about 10 to the minus 12 grams. Those are the predictions. The measurements are that we actually see no carbonaceous dust inside the heliosheath and pause in the heliosphere. And we only see a drastic rise in the number of dust particles measured about 10 to minus 15 grams is where it starts. And it comes up and then it asymptotes out at about 10 to minus 12 grams. Very, very different reality measured. So what's going on here? We currently do not understand for sure. There are some arguments and models that somehow the carbonaceous dust in the local ISM is being steered around and not allowed to enter through the heliosheath and pause. It gets charged maybe, and it gets draped around the system, but does not penetrate into our sphere. There are other models that argue that somehow the local carbonaceous dust has been destroyed from the solid. The carbon has removed from the solid phase and been enhanced in the gas phase. And Slavin and Frisch have done a lot of good work on this. And so there's a very interesting dichotomy, if you will. And the simplest and easiest way to try and understand what's actually going on is to take a suite of instruments that are sensitive to carbon dust, carbon gas, and dust in toto, and take them through the heliopause and sheath and take them into the nearby galaxy and see what's going on there. So I've mentioned this more than once. How are we going to measure dust with interstellar probe? Well, there's two instruments. The first would be what we call a Vizier spectral mapper, or VIM. And this is a simple design based on a small sat model or mission proposal by Zemkov et al. From RIT. And it would have a 0.5 to 15 micron RF 30 to 300 imaging spectrometer, so a 1D spectrometer that could push boom across the sky and map out and get reasonably good solid-state spectroscopy of dust throughout the sky, plus 4 fat single pixels, 10 arc minutes by 10 arc minutes, big, but at very long wavelengths. They could also do the same. And they can be big, easily big, because their job is simply to map out the Zodi. They don't have spectral capability, but what they will have is sensitivity to the cold Kuiper belt dust. As I mentioned before, taking this suite of imaging instruments through the Zodi cloud will allow you to do tomography. And here you can see a little bit better pictorial, just the words I said. Here's our powers of 10 picture again of ISP moving out from the sun all the way out into the local galaxy, 3 different positions. And you can imagine the easiest way to think about this is if you're looking forward in the RAM direction. And what ISP should see is a beautiful sky, see some stars, planets maybe, Kuiper belt objects, and it'll see a bright background as it starts out from the Earth. And that background should get fainter and fainter and fainter as we move through the Zodi cloud and we put more and more of the dust behind us. We're making this map, if you will, or these images in the hemispherical shell on the sky looking out away from the sun. So you can imagine that you're going to keep, the background will get dimmer and dimmer and dimmer until finally you break through the Zodi cloud. You're at the end of it, if you will. And then suddenly the background from the Zodi, at least, will disappear. And what you're going to be left with is galactic emission and then extragalactic emission, which I'll talk about a little bit later. Once we're outside, appreciably outside our Zodi cloud, we can not only try to do this inversion and make this tomographic map and model of the cloud we just went through, but we can simply turn ISP around and use channels that are blind to the sun or not affected by the sun, long wavelength infrared channels, those big fat pixels I mentioned. And we can map directly our own debris disk and then compare it to other debris disks because we'll be outside our own system for the first time ever. So how to measure dust with ISP, part 2. Well, what I just mentioned was remote sensing, using photons to detect and determine what kind of dust is out in the sky in these 3 different regions. The second will be not only a dust counter, like flew on New Horizons for the first time through our Kuiper belt, but also a dust chemical analyzer. Dust particle will come in, will hit a plate, will ionize, will fragment and disrupt and ionize and throw out atoms. And these atoms can then be passed through across E and B fields. And different atoms will come in at different places on the detector plate. And from their mass charge to mass ratio, we can actually detect and determine what kind of atoms and the number of atoms that were in the dust. So this has a lot of very important ramifications. If you're trying to look at Kuiper belt dust, for example, we're not sure whether it's all rock or whether it's rock plus ice, because they're about equal amounts in the Kuiper belt. The ice could, however, be lost rather quickly once the particles are emitted from Kuiper belt objects, because ice can be frangible in interplanetary space under cosmic ray and solar XUV radiation. But what's important is that we don't know. We have nice models. There are arguments back and forth in the literature. Most people think it's just rocky, but there's one, models are nice. The easiest thing to do is to go out there and actually measure and collect some of this dust and measure its chemical composition. Speaking of that, here is a figure showing what has New Horizons done, the first ever dust detector ever flown through our Kuiper belt. In the upper right, you see the trajectory for New Horizons, starting from the Earth, going past the planets, out past Pluto, and past MU-69, or Arrokoth, and out into the rest of the Kuiper belt, and then into outside the solar system. And what did New Horizons detect? With a dust counter. No chemical information, but size of particles and velocity information. And what it measured was in what you see in the lower right. If you look very carefully in its log plot, there's a very steep drop off at the very close to 0 distance from the sun. And that drop off is very, very steep because that's the inner disk. That's the warm dust I mentioned from asteroids and short period comets. And if you were to follow that trend, it would simply fall off very, very steeply and come down and be very close to 0, around 10 AU or so. And that's because you'll be passing through the asteroidal dust and you're outside of it. But that's not what New Horizons measured with its SDC. Instead, what happened is it hit a plateau. Around 10 AU, out to almost 40 AU now, actually more like 50, I haven't put that point on this plot yet, is that you see what looks to be almost like a stable or a flat trend in the number of dust particles per unit volume. And that's because there's a second source of dust. And just as the asteroids support the inner dust disk, what you're seeing here is direct evidence for the first time for the outer dust disk, or Kuiper belt dust. And as I alluded, is that we clearly see that there is another second source. We see Kuiper belt dust here. But what we don't know is what is it made of. and we only have one single cord from it, and you see the error bars are not tiny. So getting a better detector, or just another detector through on a different cord, and a better one that is a little more sensitive to larger ranges of dust size, as well as sensitive to the dust composition, would be a fantastic boon for dust science in the solar system. So in summary, ISP enables many types of groundbreaking solar system, heliosheath, and galactic ISM dust science. ISP is going to measure the distribution of circumsolar dust in toto, moving through the dust cloud and then getting outside of it, turning around. It's going to measure dust in the heliosheath for the very first time. We make measurements that simply have never been done before when we have basically very little knowledge. And even with an order of magnitude estimate of the amount of dust in the heliosheath and pause, it's going to dramatically improve our understanding and our models of what's going on in the boundary layers of our heliosphere. And finally, once it's out in the local galaxy, ISP is going to sample pristine dust in the ISM for the very first time. It's going to help us understand the disconnect between models and predictions for remote sensing of the dust in the galaxy versus what's actually measured, penetrating through into our system. Measurements made out as far as Jupiter and Saturn. It's also going to do a lot of interesting and useful science. We're going to talk a little more in astrophysics section that are going to give us direct astrophysical important results from measurements of dust. So let's move right along. I've talked a lot about dust, but wait, there's a lot more we can do with ISP and this location in terms of astrophysics. And this has to do with the fact that ISP is going to move outside our Zodi cloud and into the local galaxy. So I'm going to set the stage here for a little bit, so preventing a slight diversion, is that when we look up in the night sky, we see starlight, plus diffuse galactic light, plus if we're really careful, we could see extragalactic light. But that's very hard to do because the first two components dominate extremely. Now, just to set the table, our solar system is one of 100 billion systems in the Milky Way galaxy, so we think there's about 10 to 11 stars in our galaxy. We live 2/3 of the way out from the core. You can see that we're kind of in the bottom center of the image in the upper left. So we live in the suburbs. We're nowhere near the center. Things should have started out slowly here. It took a while for our sun to form, only 4.5 billion years ago. We're about 1/3 of the age of the galaxy in the universe. We think that metals, atoms heavier than helium, have formed, and that's what you and I are made of, and our nice, wonderful rocky Earth is made of. It could not have happened right after the Big Bang, when there's pretty much only hydrogen and helium with a little bit of lithium and around. So it took a number of generations of stars to burn hydrogen and helium and create fusion ash and make the heavier atoms. However, that what we call galactic chemical evolution, that building up of heavier and heavier atoms, should have happened much, much faster near the center of our galaxy, where there was a lot more density of material. ISM material is much higher, and stars form more rapidly and evolve and turn into supernovae and throw out heavier atoms much more rapidly than they do by us. So there's a very important understanding of this chemical gradient, if you will, as it's called, galactic chemical gradient, that ISP can help us do, and I'll explain that a little bit later. When we look out in the night sky, we see what we think are on the order of 100 billion island universes, i.e. galaxies, like ours and not like ours, strewn across the sky. So we think that our star is one of maybe 10 to the 22 stars out in the universe. So we're one small little system among a huge number of systems. But we're a fantastic system. And what ISP is going to do is help us understand better how we fit into all these systems. And what is that order? Well, that order is that when we look out in the night sky, we're not only just seeing stars and galaxies in the Zodi cloud, we're seeing all the light that was ever created by all the stars and galaxies in the universe. That's a very big statement, but let me explain that statement. What you're looking at on the left here, what looks kind of like a bell or a tuba, is a space-time diagram of all the things that have happened in the universe since the Big Bang. The Big Bang is the giant kind of explosion, the whitish ball you see in the left of this, where it says primordial fluctuations. And what you're seeing in terms of the vertical scale is the size of the universe. You can see from the Big Bang, it rapidly changes into much, much bigger system, exponentially so, in a very, very short amount of time, and then it very slowly expands. And in the process of happening, the Big Bang throws out, it's just a giant explosion, forms the universe, throws out a huge number of photons, which eventually cool off from they're billions of degrees, to the 2.7 degree CMB, or cosmic microwave background, we see today. And you'll actually see that in the lower right plot are a series of bumps, which are due to the different cosmological backgrounds, which I'll talk about quickly here. The universe lasts for billions of years it takes for it to cool off from this Big Bang, and eventually it cools off enough that electrons and protons can reassociate and form hydrogen atoms. And these hydrogen atoms can clump and eventually form the first stars, and the first stars and form the first galaxies. And they form the first light, first optical light that's seen in the universe. And then you get into what's called the era of reionization, where not only do you make optical light, but you make UV light, and the UV light can reionize some of the hydrogen, and you can go from a neutral universe to the plasma-dominated universe that we know and love today. This is a very, very quick, sweeping series of statements, and I don't have the time to go into more detail. But the important thing to point out is that there is light coming and being produced in all these stages. And this light, most of it is actually scattered around the universe. Most of it is, some of it's reabsorbed, of course, but most of it is scattered around and is out there as a diffuse background. I already mentioned the CMB, if you look in the lower right, the microwave background, but there's also the CIB, which is the infrared background, which is the sum of all the optical light made by all the stars and galaxies redshifted down into the infrared that we can measure today. Then there's the cosmic optical background, which is mainly due to current stars and stars in very small redshift systems near us. And there's also UV, X-ray, and gamma ray backgrounds that have important science and physics in them too, which I don't have time to go into right now. So what can ISP do for these systems? Well, let's go back to that beautiful 25 micron infrared image of the sky, which I talked about before. I mentioned the blue Z of Zorro, if you will, or the zodiacal emission, and tracing it very carefully, look at it, is an even brighter white band going through it. That's where we live, in the ecliptic plane, inside the Zodi cloud. And things are bright here because of the local dust. Well, if we actually can move through this cloud, as we mentioned before in the dust section, and we can get outside of the cloud, if you look in the upper right, you're going to see is that the emission from the cloud, go and look at the aqua curves, goes from, if you're 1 AU from the sun, then 3, then 10, then 6, then 10 AU, you're going to see the emission in front of you is going to drop, and around you is going to drop severely. Until by 10 AU, the emission is low enough, because you're outside a lot of the dust, that you get near that red solid curve. And that red solid curve is the light that we expect to see from all the stars and all the galaxies ever formed in the universe. So simply by taking a Vizier, the visual infrared spectral mapper, out past 10 AU, out past the bulk of the inner Zodi cloud, we're going to be able to measure for the very first time directly and very well the extragalactic background light, not unencumbered by the local enveloping emission from the zodiacal cloud. So that's a strong statement. How do we know this can happen? Well, if you look in the lower right, you see a dark green curve, and the dark green curve is just a model for all the light we expect from the first galaxies and stars and up till the present day. On top of that are symbols, squares and triangles and circles, and those are the best measurements done as well as we can from the Earth, and then removing our best models of the zodiacal cloud emission and then the diffuse galactic emission, and trying to get and dig out what we think the EBL, the extragalactic background light, should look like. And what's interesting is you'll see, first of all, is that we're seeing positive results. There definitely is flux out there that is over and above the Zodi cloud flux and over and above the galactic flux. But even more interestingly is that almost all of the points lie above the dark green curve. It's about 1 micron or so in the visible and near infrared. ISPs are VIM's wheelhouse, if you will. And what's interesting and exciting about this is that means there's too much light in the universe compared to what we think should be out there. So we have tension, we have interesting physics, we know we can make this measurement, we know at the level we can make it. So all we have to do is get a good detector system out there. And this is a busy plot. I'm not going to go into too much, but let me just say is that I'm putting it here for those who want to study a little more detail. These are our best current models at the different wavelengths at 1, 10, and 100 microns about what we think we can do on these backgrounds. And what we find is that, as I mentioned before, if we get out past 10 AU at the shorter wavelengths, 1 to 10 microns, that we should be able to measure the EBL very well. Just once we're out the local, really the heart of the hot zodiacal cloud. Then if we get out past 70 AU, which is out past all of the Kuiper belt dust, then we should be able to even go out to 100 microns and look at the farther, the higher redshift signals that we see out there. So there's some really exciting physics that can be done simply by taking some good instrumentation out past the Zeekel cloud, out through the heliosheath and heliopause into the local galaxy. Now, I've just gone into some detail about that. So conclusion 2 is that ISP enables unique studies of galaxy stars and galaxies and of the formation of our universe. And I just talked about the extragalactic background light, so I'm going to go through that quickly. What I didn't talk about is what we can do with interstellar dust grains and in terms of cosmology and nucleosynthesis with ISP. So I'll say that very quickly, and then I'll finish. So the second point on this slide talks about interstellar dust grains being measured by ISP using both the Vizier mapper and the dust analyzer. So in tandem, what these will allow us to do is by measuring directly dust in the local galaxy, and by directly looking at that dust with the infrared mapper, we'll be able to get ground truth for the dust with the analyzer and understand what the signals are, what the flux is from this dust using the mapper. We can then bootstrap from that across the galaxy to places we'll never go with ISP, we'll never sample directly, but because we have the ground truth in the nearby galaxy, we'll be able to use the remote sensor in a much better fashion in order to understand what's across the galaxy. Further, I mentioned galactic chemical evolution. ISP, by directly measuring local dust, pristine dust in the local galaxy, we are going to understand directly what is the composition of dust that has made it out this far or was made in this region, and what are the heavy elements in that dust. Finally, going back to the lighter elements, by measuring them, and because they haven't changed much over the course of the universe, by looking at the deuterium and the tritium and the helium-3 and the helium-4 abundances in the local medium, in the pristine galaxy, using both ISP's dust analyzer and its neutral gas spectrometer, separate talk, separate discussion, we're going to get really good measurements on cosmological species that were made in the Big Bang. And so ISP can also do cosmology directly by chemical measurements. So I hope this has been a whirlwind tour. There's way too much to talk about in the course of half an hour. But there's a lot of very important science, and it's all about location, location, location. Simply by taking two new, focused, optimized instruments through these different regions, from the heliosphere, through the heliosheath and pause, and into the local galaxy, ISP is going to do some fantastic science. Transformative science, unique science. So I hope you understand and agree with me on this point. I hope you're excited about this like I am. And if you are, please contact me and contact us. And if you'd like to serve on our committee or work with us and you have a lot to bring, please talk about that with us too when you send us an email. So thank you for your time and attention, and I look forward to hearing more from you. Take care. Bye now.